morning, everyone. It's great to see that so many of you are interested in a material that's about like 2,000 years old. So the Chinese were doing linear algebra, I think, actually like 2,100 years ago. 2,100 years ago. So it's very inspiring to see that these things that all these great minds developed a long time ago are still like useful for us and useful tools that we use every day. So today, linear algebra, for those who do not know what it actually is, it's a branch in mathematics that deals with matrices and vectors. That's basically all I want to say about the definition of linear algebra. But you could say, like, why linear algebra? Well, Morpheus already said it. The matrix is everywhere. It's all around us, even now in this very room. Okay, so what does that actually mean? Well, it is actually everywhere. So, for example, I'm just going to give a few examples of applications of linear algebra now. For example, Google, the first search engine they built was solely built on linear algebra. So PageRank, so now they developed it into something like better and more complex. But the first search engine, basically they represented the whole internet as a matrix, and they did some like linear algebra tricks, and that's how they came up with like good search results. So this paper is really highly recommended. It's kind of like explains how it actually works. It's called the $25 billion eigenvector that like basically made Google big. We can represent images as matrix, as many of you probably know. We can represent text in a matrix that you can say like, okay, each column is like a piece of, each row is like a piece of text, and the columns indicate which words are in the corresponding piece of text. And in data science, it's pretty much everywhere. It's used for linear regression. We will see that later in this talk. It's used in deep learning, computer vision, multivariate statistics. If you think of like principal component analysis, for example, and also in natural language processing. If you think of topic modeling, for example, that heavily relies on linear algebra. So what is the purpose of today? It's going to be very non-rigorous overview of linear algebra. It's more to give you a bit of an intuition and a bit more like comfort of linear algebra to get if you in your daily work touch upon these subjects, that you have a bit of a better understanding of what these things are, like matrix multiplication, matrix decomposition, those kind of things. So it helps you in the end to understand, analyze, debug, and develop models and algorithms used in data science. So we're basically going to do three things. First, we're going to do a short like primer on matrices and vectors, like what are they actually, how does matrix multiplication work, so the very like fundamentals. Then we're going to do like the geometry of basically linear regression. It's going to be quite interesting, and then we end with matrix vectorization. And if time allows, I will show that actually the second and the third topic are actually really intertwined. They're really dependent on each other, if you want to call it like that. So let's start with the vectors and the matrices. So if you ask, for example, a computer scientist what is a vector, he would just say like, it's just an array of anything. It's just a list of objects, basically. So here you see a small example of that. If you ask to a physicist what is a vector, he would say like a vector describes the force or velocity of a physical object. That's maybe what you remember from, at least what I remember from doing physics at high school. You had these vectors that indicated how some object moved or whatever. We will go for like the bit of a more like mathematical definition of vectors. It's like gives us the most structure to do cool stuff. And it's like a vector is a coordinate relative to the origin. So in this case, you see two-dimensional plane, and it basically indicates so where this let's say dot is in the plane. And of course, this generalizes to higher dimensions. So in 3D, you can still make some sort of like think of how it looks like, but in higher dimensions, all those things works. Basically always the same. So what is then a matrix? A matrix is not more than a collection of vectors. And if I talk about a vector, I mean a column vector, so the vertical one. And what is then a matrix? A matrix is basically, you can see there's a function that maps a vector to another vector. So it takes as input a vector and gives as output a vector as well. We will see an example of that in a minute. But before going there, like how does it actually work? So if you have a matrix, I hope this works. If you have a matrix, you multiply it by a vector. What you're actually doing is taking a weighted sum of the matrix's columns. I really hope that someone would have told me this like 20 years ago when I was like in high school, because this is like the most, at least for me, the most useful explanation of what matrix vector multiplication is. You see it here. You just take a sum of the red, the blue, and the green column, only you weigh it according to the corresponding elements in the vector. So this also means, like, if you do this, then the number of columns in the vector should be equal to the number of elements in the vector. This clear so far? Yeah. So we're going to illustrate now how this matrix vector multiplication works by rotating this image by 90 degrees, because clearly this image is rotated and we would like to point it upwards because it's not of any use now. So what we do, we represent every pixel in this picture by a vector. So it's like the first element of the vector is the x coordinate, so it's like on the horizontal axis. The y coordinate is the vertical, let's say the vertical, let's say place, and then the third one is the grayscale. So that indicates how gray, how black, or how white this pixel is. So then this is an example. So for example, there's one pixel over there. It's represented by this 4000, 2025 vector. So we want to rotate this thing. So it turns out that this matrix rotates each vector by 90 degrees in the counterclockwise direction. So how can we see that? Actually, the derivation is down there. So say that you multiply this matrix by any vector. This is just the matrix vector multiplication that we saw on the previous slide. So we're summing the columns, and you end up with this one. So the x and the y are flipped, and the y is multiplied by -1. Might still be a bit abstract, but let's see what it looks like. Say that you have a vector here, is 4, 1. If you then pre-multiply by this matrix, it kind of like it gets rotated by 90 degrees. So this we can now apply to this picture. This picture consists of 24 million pixels, and we just apply this matrix to every pixel in the picture, and then we end up with a Big Ben pointing upwards. Needless to say, this is like the most inefficient way to rotate the picture, because it takes like 5 minutes on your laptop to do all those matrix multiplications, but it's just for the sake of illustration. Yeah? This is also a good point to explain the matrix inverse, at least the intuition behind what a matrix inverse is. So here, I'm not going into details how to compute the matrix inverse, but the matrix inverse for this particular matrix is exactly the opposite transformation, so back 90 degrees. So that's like it's just a transformation in the opposite direction. So if you would apply the inverse here, you would end up with a rotated Big Ben again. Yes, so now we're going to the geometry of least squares. I think this is a very good topic for the purpose of this talk, because it involves a lot of like things in linear algebra that you come across often. So we're going to use matrix multiplication, vector norms, orthogonality, matrix projections, those kind of things. And the good thing is everyone knows linear regression, so it's kind of like, I think, easier to get your head around some of these topics. So we're considering this example. We have like a linear regression model with 3 observations. So there's like 3 coordinates in the 2-dimensional space, and we're trying to fit this red line through the data, basically. So this is just no frills linear regression. And we observe the data, and we're looking to estimate beta 0 and beta 1, basically. That's the whole point. Beta 0 says like, okay, where does the red line hit the y-axis, and beta 1 sets the slope of this line, basically. So what you could do is, okay, we come up with some score function, a mean square error, for example, and we're going to minimize the error that we are, we try to minimize, choose the beta such that this objective function is minimized. Today, so you can take like derivatives and do all the algebra and whatnot, but we go for a geometrical approach. And it might be a bit abstract at first, but I really think it's an elegant way of looking at this thing. So bear with me, but oh no, first we have to do this, sorry. So what we first do is write this linear regression model into matrix form. So we basically just, what we are doing here is, as Vincent likes to call it, we're just saving ink. So we're collapsing all these y's into a vector, we call it y. We're collapsing all the x's into one matrix x. So this is just rewriting it in a, like, let's say, a more efficient way. And if you do this matrix vector multiplication thing again, then you see that you basically end up with the same things, but just written in a different way. Yes, so if the point is, if we come up with some estimate of beta hat at some point, then we can just make a prediction, let's say, for y by just doing the matrix multiplication x times beta hat. So that's so far. So how does this geometrical interpretation of linear regression looks like then? Well, it looks like this. I'm going to take some time to explain this. You can think of this plane as a piece of paper like in front of you. And this plane actually represents all the estimates we can potentially choose. So every point in this plane represents with a beta, so it also represents with a, let's say, prediction for y. So we can pick any point in this plane. However, there's this y that we try to model. This y sits above the plane. Why is it above the plane? If the y would be in the plane, there would be a beta that would be a perfect fit. We see that later. So this y is above this plane, and we're trying to find a point in the plane that is as close as possible to y. Well, that's this one. So that's the one that is, let's say, perpendicular to the plane. That is where that pertains to the beta hat. That's like your best choice for y. So let's get into detail a bit more. So this is what I just said. So if this red vector would be in the plane, we could come up with a beta hat that fits y perfectly. And the best beta hat, that's the the green one, that is the one such that E, which is the arrow that you make, is y minus x beta, is orthogonal, but orthogonal means perpendicular to the plane. I really like this picture, but you may not. But I found it the first time super, because we're going to end up actually, we're going to show actually what the best beta is right now. So we have this notion of orthogonality. What does it actually mean? There's not going to be a lot of mathematics in here, but we have to do this, otherwise we will get stuck. But the idea is that you have two vectors that point in very different directions. They are like perpendicular. And this is basically what orthogonality is. How does it work? So if you have two vectors, v and w, they are orthogonal if v transpose w is equal to 0. The transpose is just flipping the vector to a row vector, basically. So this is the condition. You have v and w. It's like a red and a blue vector. And basically, if the sum of all these elements is 0, then they are orthogonal. They point in different directions. Basically, you can think of it as all these terms, they are like cancel out. So it's called orthogonality. Anyway, so this condition that we have here, that we are looking for this beta such that E is orthogonal or perpendicular to the plane, is actually that condition over there. So it's just we say like, okay, X should be perpendicular, or the plane should be perpendicular to the arrow that we make. Then we can do some, so it's good to notice one thing on the side, that we are actually minimizing the length of E, and the length of E, that is actually the length of a vector, we call that the norm. And if you write it down, it's actually what we are doing, but that's maybe not surprising, is we are minimizing the root mean squared error. But this is just a different perspective to it. And now we can just do some, basically with matrices you can also do some algebra, so I won't go into detail here, but you can do some algebra and then end up with your estimator beta hat, and that you can just compute by using NumPy, for example. So as an alternative, you would, this is an alternative way of thinking of linear regression and coming up with the beta hat that is the best fit to your model. The second thing I wanted to talk to today was, matrix vectorization, because it is used in machine learning and data science actually a lot. So matrix decomposition is about decomposing a matrix into other matrices. So for example, if you have a matrix A, you might decompose it in B and C, and it can be like B times C or B plus C. Why would you do that? For example, data compression, we will see that in a bit. Numerical benefits, because it may be faster to use a factorized matrix. And often it also provides insight into the structure of a matrix, that we will also see in a bit. There are many matrix vectorizations. Go look on Wikipedia. The list is long, and they have all different kinds of properties and those kind of things. But today we will look at singular value decomposition because it's, I think, the most famous and most used matrix decomposition out there. It's used in natural language processing. It's used to do actually principal component analysis, data compression, linear regression, and for recommender systems as well. The people that won the Netflix prize, I think, they used singular value decomposition, or at least an approximation of it, to win this prize, I don't know, 10 years ago or so. So this is a bit of a primer to see what we are working towards, and I will explain after this how we get here. This is the picture of the Big Bang again. Sorry. And basically what you see here, so this, I don't know, it was a mistake, but basically the fifth one is a sum of the first 5 ones. So we can decompose the picture into different layers, and then you see if you combine them, you end up You might think, oh, this is a bit of a shitty blurred picture, but we are using only 0.04% of all the data. So that's the thing here. We can decompose the picture, we can like pull it apart, and we can save a lot of, let's say, memory by that. And how does this actually work? So any matrix, so this is an example of a 4x3 matrix, you can decompose in 3 matrices. They're often called U, S, and V, but that's just up to anyone to name them. And yeah, so you decompose them in U, S, and V. U is like a full matrix, V is a full matrix as well, but S is like diagonal. So only the elements on the diagonal have a value, the other ones are 0. You might think, okay, I mean, like, why is this useful? Well, it turns out that this U, S, and V have special like properties that we can use to do data compression, for example. This is just doing so this step is just doing basically matrix multiplication. So what we see here is that this is equal. What you get if you take a column vector and you multiply it by a row vector, you get a full matrix. So it is basically the sum of 3 matrices, and we will see now why that actually helps us in any way. Because you might think, oh, why do we do all this? As I just said, this U and V, they have special properties. The norm or the length of each column of U and each row of V, they have a length of 1. So how does it help us? If you do that multiplication, so the column times row, you get a matrix. It kind of tells you that each element in that matrix will not be very, let's say, large, because the length of the column vector is 1. So the elements are typically smaller than 1, if you want to call it like that. And this blue one, so that comes from the diagonal of this S, they are larger than 0. So basically, this blue one, that kind of like determines the magnitude of the matrix. Because the elements of the green one times the red one are all like small. And then it's the blue one that determines, okay, how large are the numbers going to be in this matrix. And this is super super useful. Because you could say, I'm only using the one that has the blue one that has the largest value. And I throw away the rest. Because this is the one that has the largest value, that's the one that matters most. Also, but it's like on a side note, each of these, for example, the columns in the green one, in U, they're orthogonal to each other, so they point in different directions. So each column contains very different information. That's like at least how I try to convince myself how this works. So, for the Big Ben, if we do this whole thing, by the way, these blue values are called singular values. You might have heard of them at some point there. So if you do this whole trick, but then for the Big Ben, and you only take the one that corresponds with the largest blue value, you get the picture over there. So it's like let's say you can say like the contours of the tower that matter are like the most important for this picture. You see that, okay, if we only use the largest singular value, then all we basically get is the position of the Big Ben, but the rest is like a bit blurry. But we are using very little data here. So what happens if we start using, okay, the code we're going to skip. This is just as a reference. If you check the slides later, you can see how this works. It's not so difficult. But how does this work if we like start adding more data? So this is the one we saw before. We only use the largest singular value, and that gives you like the location of the Big Ben. And we only using 0.05% of the data here. But yeah, it doesn't give us much either. So you would think like, okay, this is not useful. Okay, if we also add like the second singular value, it starts to look like something of a tower. Well, maybe because we know, but at least it looks a bit better. You at least see that it has a top and then there's a building. If you do like 3, you start to recognize it, but still we're only using 0.15% of all the data. So we're getting somewhere. The point is, the picture gets better really quick. That's the whole point of this exercise. You only need like not so many of these singular values to represent the picture in a meaningful way. Because this is 5. But if we increase it a bit more, we say like 10. Now we start recognizing things. We say like, oh, there's like other buildings in the picture. The Big Ben also has a clock, apparently. And still we're only using 0.5% of all the data. And this is 20, so we use the sum of the first 20. And this is like 50. And you almost already retrieved the whole picture by using only 2.5% of all the data. And if you go to 500, you basically recover almost the whole picture and still using only 25% of the data. as a side note, this exact same trick you can apply to, for example, text, and that's how you do basically topic modeling. Then the most important topics of text that correspond to the largest singular values. So this is how you can also apply this to, for example, natural language processing. So it's funny to see that this technique is so generic that it works in many applications. But that we don't have time to discuss that, but I think it's super useful. So this whole idea that only the largest singular values matter, I tried to plot it here. What do we see? On the x-axis, you see these singular values. So this is like if we go back to this decomposition. So I took all the ones in the blue matrix. So that's the values that indicate what matters the most. And I put them in this plot. And on the y-axis is their value, and it's in a log scale. So you see that the first singular values are around like 10 million or so. And that is where you really already start to see this tower coming up, or the Big Bang coming up from this picture. But then you see like the value of these singular values, it declines super fast. So already like the 500th largest singular value is like around, 10,000 or so. So already compared to the first few ones, it doesn't really do much. So that's the whole idea of doing the singular value decomposition. So now I like to go back actually to the geometry of least squares, because like, I don't know, 15 minutes ago we had this whole thing about the geometry of linear regression. I hope you still remember it. So we had this picture. And after quite some, let's say, reasoning and some little bit of algebra, we ended up with this thing. And yeah, so you might think like, okay, but we are finished here, right? Well, the whole point is if you do, for example, in sklearn linear regression, so first let's say, so you could do this, so you could actually compute this in NumPy. So you just do like NumPy, linear algebra, the inverse of x transpose times x, and then times x transpose y. So you could think, well, that's fine, we're finished. Does anyone know why this is not a good idea to do this?
Inverse is bad.
Inverse is bad. Inverse is really bad. Yeah, if time allows, I have some examples, but as one of the messages I like to say here, try not to invert matrices numerically, because it's numerically unstable, as we say. What does it mean? If you invert a matrix, you're just not going to get the real like values. It's going to be distorted. So if you can not invert matrices numerically, always not do it. So this is the reason why this is like super interesting, I think. Oh, sorry, actually, to compute this, for sklearn to compute this, they use singular value decomposition. So that's super surprising. So first we use singular value decomposition to do this whole like image trick. And as it turns out, sklearn also uses singular value decomposition to compute our regression coefficients. So how does that work? So we start with this estimator that we derived, the beta hat. What actually is happening is that they do a singular value decomposition on x. This is numerically very stable. It's not super fast though, but it's numerically stable. Then, this is homework. You fill in the result of the singular value decomposition in the beta hat. You have to do some algebra, maybe fun on your way back. As a hint, it's a super special property that for V and U, it turns out that the transpose, so flipping it by 90 degrees, is the same as taking the inverse. And this is quite special because this is normally not the case, but that property you can use to derive that the beta is actually then equal to this. So this is how, if you do linear regression in sklearn, this is what happens like under the hood. So they do a different factorization with either singular value decomposition or I think QR decomposition, it's a different one. Anyways, it's matrix factorization that sklearns to compute your regression coefficients. So what did we do? First of all, we did a geometric interpretation to linear algebra. We talked about matrix vectors, matrix multiplication, norms, orthogonality, least squares estimation, and matrix factorization. I see that I have some time left. Oh no, first I have to recommend this one. So it's good that I have some time left. These are two sources that are highly recommended if you like this stuff. The first one is like a YouTube, let's say YouTube, how do you say, playlist or whatever, list of videos. It's made by, it's called 3 Blue, 1 Brown. I don't know how we did it, but it's like a visualization of all kinds of very abstract linear algebra topics, like eigenvectors, eigenvalues, but also matrix decomposition. Like basically, it starts from the very beginning, and it ends up all the way in very complex things. This is really as if you are like in the matrix. I don't know how. Apparently, he open sourced the code how we made it, because it's like a super cool visualization. And there's things that I've been using for years, also during my PhD, that I only like really understood after watching those videos. Then the second one, and this comment is super funny. So it says, "Who's the monster that taught me matrices but forgot to tell me about their origin and beauty?" So that hits the nail for me. The second one, if you want to do more like a course style thing, there's now a fast AI course on numerical linear algebra. It's also really good. I actually landed quite some things from that course also for this talk. I want to say thank you. If time allows, I want to say one more thing about numerical, unstable matrices, because the time allows. So you might think, like, why should I not invert matrices numerically? A very good example of a matrix that is where shit goes totally bad if you invert it is the Hilbert matrix. So it looks for 3 dimensions. You can kind of like see how it propagates, but if you can expand it to more, it's basically, well, you kind of see the structure from it. If you invert this thing, then stuff goes wrong. So I do have time, so I will do it. So you expect, so this is the first observation, you expect if you do like A inverse times A times V, that you end up with V again for any vector. Think of the picture. If you rotate it 90 degrees and then take the inverse and rotate it back, you expect to end up with the same thing again. Hey. Oh no, the code is gone. Oh, this is stupid. Anyway, so what you do, I can tell what it returns is out. So if you do this for a matrix of 10 by 10, you make the Hilbert matrix using a SciPy linalf. So what you expect if you do the inverse of A, you see it at the bottom. If you multiply the inverse of A by A times V, and V is just a vector of ones, you expect to return a matrix of ones. Well, the thing is, try it at home. You don't get back a vector with ones. It's going to be like already large deviations that you see. So I think I print the minimum here. It's like 0.99 or so. So you already have like a huge deviation from 1. So this is just yeah. That was just the last message on inverting matrices numerically. So thank you for your attention. I hope you liked it. And if you have any questions, I think we have time for questions. Yeah.
Yeah, put your hands up if you've got any questions. Nobody? Is there anything else you want to talk about? Because there's a lot of time.
Yeah, no, I admit I was already wondering, like, what are people even going to ask? Because it's not really, it's more like a lecture than
Anything you want to plug?
Yeah, so we have a very cool competition going on with Go Data Driven. You can win a Lego box. Maybe you saw it. So we have a stand over here at Go Data Driven, our company, and we have a kind of like set up a competition in which you can win a Lego box. There's a few hours left, so if you like to solve a very difficult combinatorial problem and win a Lego box, then go for it. It's a super cool thing. Yeah, for the rest, I don't think I have much to tell, so then we can just go to... Yeah, no, there's nothing.
All right, let's give him a round of applause. Oh, no, hey, go.
What's the software you use to convert the markdown to the presentation?
Yeah. I used it for the first time for this one. I really liked it. It's called DEXet. Sorry? DEXet is called. Yeah. The cool thing, yeah, we have time anyway. The cool thing, you can choose like themes very easily, and then it starts to look, it looks amazing even if someone like me who is like really shit at making slides look nice, then it really helps you. And it also helps you to not to put too much on a slide, because you basically, it just doesn't fit. If you just keep adding stuff, it will just fall off the slide. So that kind of like prevents you from having very long lists of stuff.
Okay, now we,
How do you spell it? DEXet.
DEXet. So,
DEXet.
yeah, exactly. Yeah, it says it here, I think.
DEXet.
Vincent.
So we saw sort of inverses and like SVD and that sort of thing. Is there any sort of other like topic in linear algebra that's like super cool not to ignore?
Eigenvalues, I think. This is the one thing I did not have to, well, it turned out I would have had time to do it, but I think eigenvalues are, I think, most used and least understood, like at least from an intuition perspective. And they pop up basically everywhere. It's unbelievable. But I would really, and then I would recommend the YouTube videos because there they have a super good explanation of how eigenvectors and eigenvalues work and what they actually are. They're actually very much related to singular value decomposition. So that's what I would recommend. Yeah, I think so, yeah.
Oh.
Very good talk, thank you. Could you give us some examples to how this is applied? Maybe a bit more advanced than the one that you showed, or example from your own experience where this was really important for you to like save you a lot of time. And
I think where linear algebra is most used, at least, is in implementing computations fast. I did not want to go in there because I think for me this was more interesting. But the idea that by vectorizing code, so for example by using NumPy, that is very, for example, if you do like these deep learning things in TensorFlow, that's where there's a lot of value from like computational gain by using linear algebra and putting stuff in matrices because of the way they are like implemented in, for example, NumPy, they're like super fast and they run on, I don't know, some low-level code. So that is where they are, I think, mostly, where linear algebra is mostly super useful by getting rid of for loops and vectorizing stuff and making sure that things go super fast. Other things is, for example, what linear algebra is also often used. I don't know if you're into like Markov decision processes and Markov processes. These kind of things there is like also often used because then the matrix. I'm not going into detail too much, but the linear algebra is also often used. Yeah, I don't know other things I'm missing, but.
I'm doing something in my talk after.
Oh, okay, yeah. So yeah, just stay and. Vincent will give you some other examples, but yeah, that's mostly it.
Okay, let's give him a round of applause, please.
Cheers.